Hello everyone, I am going to attempt to explain how to solve this double integral. So I want to do first a background what a double integral is, or what interpretation of one is. Suppose we have a surface in three-dimensional space, and that surface in this case is given by z equals e to the x squared. And so I'll just try to draw something that's not really that great of a picture here, or that not all that well done, but somehow we have this surface like this. Now, the way you can interpret a double integral is the volume of the region below this surface. Now, the surface actually goes on infinitely, and I drew it so that it sort of is bounded, so it doesn't. But in fact, just by itself, z equals e to the x squared goes on infinitely. Okay, so but in this particular problem, this double integral, the domain of the function z equals e to the x squared is a bounded region, and it turns out that region is a triangle, and we'll see why in a moment. But this region, which is the domain, is a triangle, and so when we evaluate the double integral, what we're doing is we're evaluating or finding the volume of the region that is below the surface and within this domain D, which is a triangle. So, I mean, it's these three-dimensional pictures, is my little excuse, but they're notoriously difficult to draw and represent even with computers. But so we have this region above the triangle, and that's like in the floor of this solid region. I should probably say solid instead of solid region. The floor of this solid is a triangular region, and then the roof is given by the z equals x squared, and we're trying to find the volume of that. Now, a double integral can be written as double integral over d e to the x squared dA. That's pretty often the starting point. And then we start here, and then we examine the region D, and then we get a double integral with bounds. The first bound here, if I put parentheses around this first integral, that's an integral in x. It says dx, and the bounds are x equals 3y and x equals 3. So we have these bounds here. These are x bounds, and then after that, we integrate with respect to y, and we have y bounds. Now, okay, let me go ahead and then talk about what D is. So D is the region xy such that, okay, now these bounds are going to tell us what D is. We have to decipher this. Okay. The outer integral is with respect to y, and y then goes from 0 to 1. So y is bound by 0 and 1, and then this inside integral is with respect to x, because we see dx there, and x goes from x equals 3y to x equals 3. So we write 3y below x and then above 3. And so these bounds represent functions x equals 3y and x equals 3, and those are bounds on D. And these, as shown in the picture, the domain is in the xy plane, and then in three-dimensional space, we can express it on the xy plane there. But okay, let's go ahead and sketch this. So x equals 3 is a vertical line, and then x equals 3y can be written as y equals 1/3 x. That's in y equals mx plus b form, so we see the slope is 1/3 and the intercept is 0. So we can sketch that sort of simply. And then we also look at the bounds on y. Y starts at 0, so here's y equals 0, and then it finishes at y equals 1. So on the left, we have x equals 3y, On the right of this region, we have x equals 3. And therefore, the region that we have for D that I'm coloring in blue here is, well, here it is. Okay, so there's D. Now, this all seems fine, and the question is, well, why did I even do this? Well, the reason is I did this is because when I get to this double integral and I have these bounds here, then I start integrating using single variable calculus techniques. I integrate e to the x squared dx. So I start on the closest one, dx is closest to the function. So I start with that dx integral, the integral with respect to x. Now the fact is that this integral, e to the x squared dx, this integral cannot be solved in terms of elementary, cannot be solved in terms of elementary functions. All right, so we cannot find this in terms of elementary functions, and that's another story of why we know that's true, but it can be, there's ways to express this with approximations, with power series, but we cannot, there is not an elementary function such that when I take the derivative, I get e to the x squared. So what we do then is something well, as the directions say, is we change the order of integration so that instead of integrating with respect to x first, instead we integrate with respect to y first. And so this integral can be expressed as first e to the x squared dy, and then dx. And the way we do that is by rewriting our characterization of D, our description of D. Now, see, D has x bounded by 3y and 3. That actually is a type 2 description. But for type 1, we do this. So for type 1, here it's still the same D, but we write xy such that, all right, we make a bound not of functions not on the x variable, bound of functions on the y variable. And so as I sort of wrote up there before, we write the top function is y equals 1/3 x, and the bottom function is y equals 0. And then for D, we bound y by those two functions. And there we go. And then we look at x, and we see x is bounded by the numbers 1 and 3, which are constant. And so then when we write our integration where we first integrate with respect to y, then we have these bounds 0 on the bottom and 1/3 on the top, 1/3 x on the top. And then for x, we have 0 on the bottom and 1 on the top, 0 to 1. So we see x is from between 0 and 1. Oh, well, looks like I did that wrong. That's super bad. Do I have to redo the whole video? That probably was bothering everybody. X is between 1 and 3. Okay, sort of. Yeah, well, anyway, there we go. So x is between 1 and 3. It says x equals 3. So x starts at 0 and goes to 3. And y has on the bottom 0 and goes to 1/3 x. All right, now I can evaluate this integral, because to evaluate this integral, I noticed that the first inside integral is with respect to y, but e to the x squared is a function that doesn't have any y in there. So in fact, that's a constant in terms of our integral with y, integration with respect to y. So we really just have this just integrating 1. And so let's go ahead and do that. So I have 0 to 3, e to the x squared, and the integral 1 is y with respect to y. And then I'll evaluate that from 0 to x over 3. And, okay, so I have 0 to 3, e to the x squared, x to the third minus 0 dx. And there we go. Then now we're thrown back to a single variable calculus integral. And it might not look that different from what we had before, but this x now makes a huge difference. It's all the difference in the world. And the reason is because x is, well, it's the derivative of x squared. It's half of the derivative of x squared. So what we can do is we can use u substitution. That's where this is all going right here. So u equals x squared. Du is equal to 2x dx. All right, and so then I have 1/2 du equals x dx. And I go ahead and work that out. So I have 1/3 integral x dx. Well, e to the x squared is e to the u. And then x dx is 1/2 du. Now, also, when x equals 0, u equals 0 squared, which is 0. And so I can put 0 down here. When x equals 3, u equals 3 squared, which is 9. So now we have sort of an easy integral. 1/3 times 1/2 is 1/6. And I have the integral from 0 to 9, e to the u du. So the antiderivative of e to the u is just e to the u. 0 to 9. So I have 1/6, e to the 9th minus e to the 0. So this is 1/6, e to the 9 minus 1. And that is the answer to that problem. We evaluated the integral. And as I said before, we can interpret that as the volume of the solid that is below the surface, given by z equals e to the x squared, and within that triangular region D. Let me see if I can zoom out before I finish this and close this, turn this off. Okay, so that's the end of that problem. Thanks.